Lesson 7. So today we're going to pick up talking about the atom itself and the atomic model. We've talked about the atomic models in general, talking about the history of the atomic models. Then we spent some time in class talking about the periodic table and its organization. Just a reminder that the periodic table groups have some special names. We talked about group 1A is the alkali metals, 2A alkaline earth metals, 7A is the halogens, 8A is the noble gases, and then we have the lanthanide and the actinide series, which are periods at the bottom of the table. Also remember that we had finished up in class talking about Mendelev's periodic table in lesson 6. We talked about all the patterns that it had based on atomic weights, based on its physical properties and chemical reactivity in compounds. And we said that elements in the same group have the same chemical reactivity and form the same predictable type of compounds. And we had all these things. Note that what we've talked about so far is the macroscopic, observable, measurable quantities and how those metals, nonmetals, properties relate to the periodic table. Today, we're now going to show you about how the periodic table also incorporates patterns of atomic structure. So we've talked about the models of the atom. Now we're going to kind of see how does that play out in the periodic table. So we're looking for how is the periodic table based on atomic structure. Additionally, we're going to talk about how elements form ions, how atoms form ions, and how we can predict that off of the periodic table. Okay, so we're going to introduce the orbit model, which is really basically the Bohr or shell model we talked about in the atoms of the model, but we're going to add in a little more detail than was in the Rutherford experiment and the Bohr experiment. Okay, so we begin by talking about the fact that we're saying that atoms consist of protons, neutrons, and electrons. And again, we hadn't really talked specifically about what a proton was, what a neutron was. Now we're going to start talking about those. All atoms of the same element have the same number of protons, which is the atomic number of the element. And we'll talk about how we find the atomic number of the element. Positively charged protons and neutrons are located in the nucleus. Remember, that was that dense core that Rutherford found. Electrons are negatively charged and move around the nucleus in orbits. That was Bohr's contribution, is that they're not just randomly there, they're in specific orbits. And that the nucleus is much, much more massive than electrons. So this is where we're picking up with the orbit model. Let's just kind of get a little more detail. So we talk about these protons, neutrons, and electrons. Let's kind of record what their properties are. So the proton is positively charged, and it is found in the nucleus. It has a mass of 1 AMU. AMU stands for atomic mass unit. The neutron is neutral. It has no charge. It also has a mass of 1 AMU. And both the protons and the neutrons, remember, are found in the nucleus, in the dense core. The electrons are negatively charged and have almost no mass. Note that 0.0005 is so much smaller than 1 that effectively we can say electrons are 0. Of course, they do actually have some mass. It's just so tiny it's not really relevant. So question 1, and I've just kind of built a little model here just to kind of look at, here's my protons and my neutrons in that dense core. Here's my electrons on these orbits outside the nucleus. If an atom is neutral, what does that say about the number of protons and the electrons within the atom? Is there a relationship? Is it random? I want you to think about that for a minute. Go ahead and pause. Okay. And if an atom has one less electron than protons, what would be the overall charge of the atom? Okay, hopefully you came up with the fact that the only way that the number of protons and electrons is significantly significantly tied to its charge. So for an atom, and an atom is neutral, it must have the same number of electrons as protons so that the charges cancel out. That's the only possibility. If an atom has one less electron than protons, so it has one less negative charge than positive charge, or I can flip that and say it has one more positive charge than negative charge, then it would have a +1 charge. Okay, so let's just kind of now go back and restate this orbit model, but kind of like build it up from all of these principles together. So the atomic number of an element is the same as the number of protons, which should be in the nucleus. So we're going to put those protons in the nucleus. And over here I'm looking at boron. And I went to the table and I found that a boron's atomic number is 5. So I put 1, 2, 3, 4, 5 protons in this center. It has neutrons. Those are those 0 charge things in the center. But we don't know how many of them. So I just put 3. But it could have been 4. We don't know. Since it is neutral, it has the same number of electrons as protons. So in other words, if I had 1, 2, 3, 4, 5 protons in the center, I have to have 1, 2, 3, 4, 5 electrons in these orbits. If there are missing or additional electrons, then this is no longer an atom, but it's an ion, and it will have a charge. And I can figure out the charge from taking the number of protons and subtracting the number of electrons. But this isn't, we're talking about atoms, so they have to have the same number. And since the electrons have a mass of about 0 and both protons and neutrons have a mass of about 1, I can count the number of protons and neutrons in the nucleus to tell me the mass of the atom. So this particular one would have 1, 2, 3, 4, 5, 6, 7, 8. So this would have this particular atom would have a mass of 8. I'm going to basically ignore the electrons because they're so small. It really wouldn't be 8. It would be 8.0002 or something like that. But I'm not going to worry about it. I'm going to say it's close enough to 8 to say it's 8. So we're going to now take this and go back to the periodic table and look at the orbit models of all of the elements on the table, the representative elements on the table. Okay, so here is the orbit models of the representative groups. Remember, the representative groups are just the A groups. And as I look at them, I'm sort of seeing these models. I'm going to ask you a bunch of questions. So I'm going to go back to the next page and ask you questions, and then we'll come back. What general trends do you observe in the atomic number as you move from left to right across the table and from top to bottom? What is the relationship between the atomic number and the protons in the nucleus? What is the relationship between the atomic number and the electrons around the nucleus for the neutral atom? And then looking at atomic numbers 1 through 20 and then atomic numbers greater than 20, is the number of protons always less than, equal to, or greater than the number of electrons? I mean the number of neutrons, sorry. What is the relationship between the number of occupied energy levels, those are the orbits or those concentric circles, the containing dots, and the period, which is the horizontal number? What is the maximum number of electrons that can occupy the first energy level, the second energy level, and the third energy level? And what is the relationship between the number of electrons in the outermost energy level and the group, which is the vertical number? All right, going back. So the first question was asking about atomic number. Note that this is the atomic number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what do I notice as I go from left to right across the table with the atomic number? Hopefully I see that as I move from left to right, it increases by 1. So it's almost like a box number. And what about going down the table? 1, 3, 11, 19. Or 4, 12, 20. Hopefully I'm noticing that they're increasing by 8, right? And also there's 8 boxes across. So I can see that this is almost like this kind of increases, almost like I'm reading a book. Another question was, what is the relationship between the atomic number and the number of protons? Okay, I see that in the center, instead of showing them as pluses, this is now just has it as a number and how many P for protons. So the atomic number is 1, and this has 1p. 3, 3p. 11, 11p. 13, 13p. 15, 15p. 9, 9p. 35, 35p. So we see that the atomic number is the same as the number of protons in the center. It also asked about the atomic number and the number of electrons. Well, these are representing the electrons. So let's look. 6, and I have 1, 2, 3, 4, 5, 6. So 6 electrons, and the atomic number is 6. 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 protons, 15 dots. And if you continue and look at all of them, it's the same. And that makes sense because the number of protons has to be the same as the number of electrons if we want this to be neutral. It asks me about the number of concentric circles, the number of orbits. So I have on this and the period, which is the horizontal number. So this is period 1, period 2, this is period 3, this is period 4. And I see on period 1, I have one circle here, I have one circle here. So I have just one orbit. On period 2, I have 2 circles on all of them. On period 3, I have 3 circles on all of them. On period 4, I have 4 circles. So again, I see that the number of orbits or concentric circles is the same as the period number. Another question it asked is, what about the relationship between neutrons and protons? And they're talking about less than 20 and then greater than 20. So let's just kind of look. I have 1 and 0, 2 and 2, 3 and 4, 4 and 5, 5, 6, 6, 6, 7, 7, 8, 8, 9, 10, 10, 10, 11, 12, 12, 12, 13, 14. So I can't really make a distinct pattern of saying that the number of neutrons is always less than the number of protons, or that the number of neutrons is always greater than the number of protons, but they do seem to be about the same. Sometimes they're equal. Sometimes there's one more neutron than proton. Sometimes, let's see, do I have a case of there's one less neutron? And this goes up up until a 20. But notice when I get above 20, when I do these 31 through 36, now all of a sudden I'm having substantially more neutrons. 31 to 39, 32 to 41, 33 to 42, 34 to 45. So I see that this is not a pattern that's true for the entire periodic table. I see a pattern up to 20 and then a different pattern above 20. So there doesn't seem to be a very strong correlation, but in general, it's about the same number for elements with atomic number less than 20, and it's generally more neutrons than protons for atomic numbers greater than 20. Okay, so we just kind of sum that up. The atomic number increases by 1 for each element from left to right, and then from top to bottom, meaning if I go from left to right first and then top to bottom. What is the relationship between the atomic number and the protons? They're the same. It's also the same number of electrons around the nucleus. And we saw that below atomic number 20, the number of neutrons is very close to the number of protons. Above atomic number 20, there are several more neutrons than protons. We saw that the number of orbits or concentric circles is the same as the period, which is that horizontal numbering, the row, and that the maximum number of electrons, we didn't do that one. Let's go back and do that one. And the relationship between the number of electrons and the vertical. Okay, let's go back. Okay, so now, what was the first one we were looking at? Was the maximum number of electrons. Okay, so if I'm looking at this first level, I have 1 here, I have 2 here, I have 2 on the innermost level, 2, 2, 2. It looks like when I look at these more complex models, that first level can only hold 2. I don't see anywhere it's more than 2. Let's look at the second level. And again, it's a little hard because it's changing here. I have 1, 2, 3, 4, 5, 6, 7, 8. But now when I look at these have 8 in the second level, 8 in the second level, 8, 8, 8, 8, 8, 8. So it looks like 2 for the first orbit, 8 for the second orbit. I see a whole bunch in the third orbit down here. So let's kind of look at these. If I count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I can count others as well. So it looks like that third level can hold a total of 18. But notice that it doesn't start filling past 8 until it gets after 20. So it only has 8 in this 1, 2, third level. So it has 8 here, and all of a sudden it jumps to 18. But of course, we've also jumped from 20 to 31 because this is only showing those representative elements. Remember, we're not showing the B group elements. So there does seem to be a pattern. The last pattern was talking about the group number, its vertical number, and the number of electrons in the outermost orbit. So let's look at group 2. In this one, the outermost orbit has 2. In this one, the outermost orbit is 3, but it has 2. In this one, the outermost orbit is 4, but it has 2. Let's look at 5, group 5. 1, 2, 3, 4, 5. And again, now the outermost is no longer orbit 2, but it's orbit 3, but I have 1, 2, 3, 4, 5. Here I have 1, 2, 3, 4, 5. So the maximum number of electrons, I can have 2 in the first orbit, 8 in the second orbit, 18 in the third orbit, but below atomic number 20, there's only 8 seen in that third orbit. I should say this should be third orbit. And the relationship between the number of electrons and the outermost energy level and the group number is that they are the same. So I can make a prediction about how many electrons are in that outermost orbit based on what group number it is. Okay, so let's try a couple questions. Which of the following statements are consistent with your observations regarding the atomic structure in the periodic table? Is the atomic number equal to the number of protons, also the number of electrons of an atom? Is the period number equal to the number of occupied energy levels of an atom? Is the group number equal to the number of electrons in the outermost energy level of the atom? Are all atoms in nature are neutral because they have equal numbers of protons and electrons, or are all of the above? Well, I feel pretty confident about this one. Atomic number is equal to the number of protons. We definitely saw that, and it was equal to the number of electrons. I also feel confident that the period number is equal to the number of occupied energy levels of an atom. That's how many circles or orbits I saw. And the group number is equal to the number of electrons in the outermost energy level of an atom. I feel good about that. So once I have 2 that have to be true, I'm in this all of the above. So hopefully we recognize this is all of the above. Okay, so let's just kind of summarize again. If I'm looking at an orbit model, or I want to make an orbit model, I can get a lot of the information I need from the periodic table. Or if I'm given an orbit model, I can tell where it belongs in the periodic table. So again, each ring is called an orbit. We'll also call it an energy level, and that the number of rings that I need to draw is equal to the period. The central blue circle represents the nucleus. It shows how many protons I have, and the protons have to be same as the atomic number and how many neutrons this atom has. But atoms of the same element can have different numbers of neutrons. This is showing me a particular one, but it could be 40, it could be 38, it could be different numbers. I did have a pattern of the relationship, but really we're not going to be able to make a whole lot of predictions about neutrons. These dots are representing electrons, and the number of electrons in the outermost orbit is equal to the group number. And I also know that I can figure out the total number of dots should be 31 because this has 31 protons, so it should have 31 electrons. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. I also can see where they go is not random. The first level has 2. The second level can have 8. So that makes a total of 10. The third level can have up to 18. So that gets me to 28, and then 29, 30, 31. So I could make a prediction that because there are 3 electrons in this outermost level, that this is in group 3. I could make a prediction of what element this is based off its protons as its atomic number. I could go find it. I could say this should be in group 3, but it also should be in period 1, 2, 3, 4. So I have lots of ways of looking at this model and telling me where this belongs in the table. Or if I'm given a position in the table, I can tell you what the orbit model looks like. Now this is a similar table. However, this is now moving on, not talking about the atoms, but talking about the ions. So this is predicting the ion formation. And again, we're going to look for this and look for the patterns. All right, I see that hydrogen loses 1 electron and becomes H+. So this is going to lose 1, and I'm seeing an arrow going off to show that it's losing. I see helium, which is 2, does nothing. No electrons gained or lost. 3 loses 1, becomes lithium plus ion, and it's going to be, it looks like it's this outermost one is going off. Beryllium loses 2, becomes beryllium 2+, so it's losing this one in the outermost orbit. Boron loses 3, 1, 2, 3. So I'm seeing a pattern here, right? Carbon loses 4, 1, 2, 3, 4. Oh, whoa, my pattern broke. Nitrogen gains 3. So it gains 3, and it looks like they go in this outermost orbit. And oxygen gains 2, and they go in this outermost orbit. Fluorine gains 1, and goes in the outermost orbit. Neon doesn't do anything. No electrons gained or lost. Okay, let's just stop and take a look. If hydrogen loses this electron, how many electrons are in this outermost orbit? It'd be 0, right? And helium, it says no electrons gained or lost. Lithium loses an electron. So when I lose an electron, how many electrons are in the outermost orbit? None. So in other words, is it even occupied? No. So in other words, how many electrons would it have as an ion in the outermost occupied orbit? Well, if it lost this electron, then the occupied orbit would be orbit 1, and that would have 2 electrons in it. If I lose these 2, note that I've emptied out this second orbit, which means that the highest number, now the valence orbit, which is defined as the highest occupied orbit, would be orbit 1, and it has 2 electrons in it. If I lose all 3 of these, notice again, the occupied orbit is that innermost 1, and it has 2 electrons in it. So it looks like when it loses the electrons, it loses all of the valence electrons, and then I'm left with 2 in the occupied. It would be a valence of 2. Let's look at aluminum. It loses 3, and again, when it finishes, it's going to have its highest occupied orbit would be orbit 2, and there will be 8 electrons in it. Same thing with magnesium. Let's flip over here to the gain side. When I look at nitrogen, when it gains 7 electrons and they go here, I will now have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second orbit, which is the highest occupied orbit. If oxygen gains 2, I would have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that highest occupied orbit. Fluorine, once it gains 1, I'll have 8. Neon already has 8 in its highest occupied orbit. I see that happening down here too, right? So I'm starting to hopefully see this pattern. Let's kind of reveal it here. I do need to sort of remind you, I may have been talking about the word valence without saying what that is. So when an atom has a charge because it has gained or lost electrons, it's called an ion. Notice that we only gained or lost electrons. We didn't do anything to the protons. Electrons that are furthest from the nucleus or that reside in the highest, and I should put in the word occupied energy level, are called the valence electrons. So when we had first looked at the atoms, the valence electrons was the same as the group number. But when it's ions, it sort of can become a little different. All the other electrons of an atom that are not the valence electron, we call the core electrons. So I've been sort of answering these for you when we were looking at that, but I want you to take a moment and complete this table. It's asking how many valence electrons are there initially? Does the atom gain or lose valence electrons? How many valence electrons are lost or gained? And what is the charge on the atom formed? for, go through all the ones in group 2A and group 3A and group 4A and complete this table based on this right here. I'll let you can pause this and try to complete that. Okay, so hopefully this is what you got. That if you're in group 2A, it has 2 electrons initially, and note that the number of valence electrons it has initially is the same as its group number. For groups 2A and 3A, it loses its valence electrons. So I lose 2 for group 2A, I lose 3 for group 3A, and become a +2 or +3. On this side, so 4 seems to be the break point. And note they didn't even ask me about this because it's a little weird. So I moved to 5, 6, 7, 8. 5A now gains, 6A gains, 7A gains. So these higher numbers will gain, and they gained 3, 2, or 1 to become a -3, a -2, a -1. 8 did nothing. Now remember, I just want you to kind of pay attention to 5 plus 3 is 8, 6 plus 2 is 8, 7 plus 1 is 8, and 8 seemed to be a happy number. Again, what about this? When I lose 3, I now have 0, right? And I lose 2, I now have 0. So since these were gaining, I would add them. Since these are losing, I would add them. But remember, once I have 0, that level is no longer occupied, and so technically the lower level below it, which is full, is now considered sort of, it will have a full outermost energy orbit. So which electrons were lost or gained in the formation of the ions? Was it the core electrons or the valence electrons? Hopefully we saw it was the valence. Why are ions positive when they lose electrons and negative when they gain electrons? Think about that a minute. Remember, electrons are negatively charged. So if I lose a negative charge, that's like minus a minus sign, and it's going to become a positive ion. And when I gain a negative charge, it will become more negative. And what is the relationship between the number of electrons lost and the number value of the charge of on a positive ion? In other words, I'm not looking at the positive or negative sign, but just looking at the value. And again, it's the same because if I've lost 3 electrons, I have 3 fewer electrons than protons, and so it should have a +3. Okay. So let's kind of wrap up what we talked about with a couple of questions. Which of the following statements are consistent with your observations regarding ion formation in the periodic table? Metal atoms tend to gain electrons to form positive ions. Non-metal atoms tend to lose electrons to form negative ions. When atoms lose or gain electrons, the arrangement of electrons in the ion resembles the arrangement of electrons in the nearest noble gas, or all of the above. All right, hopefully we go back to that table where we paid attention to this and see that, remember, metals are the ones on the left, groups 1A, 2A. Some of the 4A, 3A, and 4A are metals. And they all lost electrons. So A is out. B, nonmetals are on the right. Some of the groups 3A, 4A, but 5, 6, 7, 8A are all nonmetals. And they gained electrons, so B is out. When atoms lose or gain valence electrons, the arrangement of electrons in the ion resembles the arrangement of electrons in the nearest noble gas. So this is true. Let's see what they're saying. So once I'm done adding this electron here, it looks the same as this one. Once I'm done adding these electrons here, it looks the same as this one. When I look at beryllium, the nearest noble gas would actually be 8A. So 4 is closer to 2 than it is to 10. So if I lose 2, then I have 2 in the in the first orbit, and it looks the same as this. In this case, if I lose 1, 2, 3 aluminum is closest to 10, and I would have 8 in the second level. So once it has lost, it looks like this. So for when it's losing electrons, it's going to look just like the noble gas that was prior to it, you know, lower in atomic number. And when it gains electrons, it's going to look like a higher atomic number noble gas. Remember, noble gases is this column. All right, question 2. Rubidium, atomic number 37, is positioned beneath potassium in the periodic table. Which of the following statements about rubidium atoms are correct? And I may now need to go look at it on the periodic table. I don't think that we had it on our element map, but go take a second and look at it on the periodic table. So option 1, it has 37 protons and 37 electrons. Do I need to look at the periodic table for that one? What about 37 neutrons? Where would I find that information? How would I know if it's in period 1 or not? What does the period represent? How would I know if it's in group 5 or not? How many valence electrons does it have? And are the valence electrons in the 5th energy level? So questions 1, 2, 5, and 6 do not require that I see a periodic table. Questions 3 and 4 mean I have to go find rubidium on a periodic table. And if I do, I see that rubidium is in period 5 and group 1. I also see that I already know that because it's atomic number 37, it has 37 protons, and because they said it was an atom, it would have 37 electrons too. So this statement is definitely true. But I have no idea how many number of neutrons it is. Remember, we keep talking about this. I can show a particular atom, and on that element map, it may have shown one that has some number of neutrons, but I don't know how many. They can vary. So I really can't say anything about the number of neutrons unless they tell me something more about this atom. It is not in period 1, it's in period 5. It is not in group 5, it's in group 1. And it's notorious that students will confuse these. I don't want you making that mistake. That's an easy way to lose points, and there's no need for it. On the periodic table, it clearly labels which ones are the groups, which are the columns, and which ones are the period, which are the rows. Make sure you can get those correct. It has 1 valence electron. Well, if it's in group 1, and I know that the number of valence electrons is equal to the group number, so that's true. I guess I would need to have had that periodic table for 5. But for period 6, the valence electrons are in the 5th energy level. I know that it's in period 5, and so from that I can tell that it is the number of valence orbit is the period number, so that's true. So I end up with 1, 5, and 6. So actually, I would need to know its group and period before I can answer 5 and 6. Which statement describes the ion that rubidium forms and how? Does it gain 1 electron to form rubidium minus, lose an electron to form rubidium minus, gain an electron to form rubidium plus, or lose an electron to form rubidium plus? Again, what do we already know about rubidium from the previous question? So rubidium is a metal in group 1 with 1 valence electrons, and we know that metals lose their valence electrons. And if it loses its 1 valence electron, that means it would have 37 positive charges and 36 negative charges, so it will have a +1 charge. When it loses electrons, it becomes positively charged. So the answer is D. All right, that's the end of this, but I just kind of want to go back and take a second and remind ourselves about Dalton's atomic molecular theory. This was that billiard ball theory. And he said the elements are comprised of identical atoms. All atoms of a single element have a single characteristic mass. The number and masses of atoms do not change during a chemical change, and compounds consist of identical molecules formed of atoms combined in simple whole number ratios. And now that we've really gone into these actual atomic models a little bit more, I just want to kind of fix it. So this is a pretty good atomic model. However, a couple of things that are wrong is, as we now know that there's protons and neutrons and electrons, the atoms of elements are not identical. So they some have more or less neutrons, so they won't all be identical. Also, that means if it has different numbers of neutrons, since a neutron has a mass, that will affect the mass of the atom. Therefore, the single elements do not have a characteristic mass. We'll talk more about the periodic table. I know you've been told that you can tell the mass number of a table, but we can't use that. But the number of masses of atoms do not change during a chemical change. Once I have an atom, its mass does not change. And the number of electrons may change, but remember we said the electrons don't have much mass. The compounds consist of identical molecules formed of atoms combined in simple whole number ratios. That is still true. Okay, so this is lesson 7. The homework will be based off of some of this atomic structure, and some of this is will be based off of isotopes. So the extension H kind of goes into what is an isotope. And I just want to spend a little bit of time telling you a little bit more about isotopes. So the big idea is that isotopes would be two atoms of the same element with different numbers of neutrons. So now we're starting to talk a little bit more about the fact that the number of neutrons is not fixed and it can change. So if I find two atoms that have different numbers of neutrons, and of course it's going to affect the mass of the atom because the neutron has a mass of 1, those would be, so sodium-22 and sodium-23 are isotopes. Carbon-12, carbon-14 are isotopes. Just a note that isotopes are found naturally. Under normal conditions, I can't add neutrons to or subtract neutrons away from an atom to make an isotope. I go find them and I say, oh, here's one that's a carbon-12. Oh, here's one that's a carbon-14. But I can't make a carbon-12 into a 14 or vice versa, except for nuclear reactions. And we're not talking about those. So we talk about this atomic symbol. And in the atomic symbol, there are 3 parts. 1, the element symbol. That's the chemical symbol that's on the periodic table and on our element list. 2, the mass number, which is in the upper right. And this is the number of protons plus the number of neutrons. Remember, both protons and neutrons weighed 1 AMU. So adding them together will tell me the mass of this atom. And then I have the atomic number. And again, remember, the atomic number from the periodic table is defined by whatever the element is. So I'm going to say the atomic number goes in the lower left, and I'm going to say it's optional for instructors. I don't need to put it there because if I tell you what element it is, you can go look through a periodic table and determine what it is. But when I ask you to write an isotope symbol, I expect both of these numbers to be there. So again, an isotope would be 2 atoms of the same element with different numbers of neutrons and thus different mass numbers. So I'm going to see this top number changes. From that, you should be able to work on the homework. Here is an example. If I gave you the mass number, or I gave you the isotope, and I asked you how many neutrons were in the nucleus, remember, since the mass number is the number of neutrons and protons, and the atomic number is the number of protons, if I subtract off the atomic number from the mass number, that will tell me my number of neutrons. So I take the top number minus the bottom number to tell me my number of neutrons. Or if I gave you an isotope symbol and I said, tell me how many protons, neutrons, and electrons there are, I can also figure that out. So the number of protons would be from the atomic number. So again, no, I'm an instructor. I don't have to tell you the atomic number because you can look up carbon on the periodic table and see that it's 6. So if it was written in, it would go right here. The mass number is 14, and the number of neutrons is the mass number minus the atomic number. So 14 minus the 6 that I had above is 8. If this is an atom and uncharged, then the number of electrons is the same as the number of protons. So I just copy it. It's 6. And this should be a pretty good working practice for you to do the homework.